here so far. Now let's recap about KD and KP. Now the only two ways that they can give you to determine the slots is they'll say they've got 36 slots. That means you've got 36 slots in 360 degrees. So the slot angle Psi is 360 divided by 36, which is 10 degrees mechanical. Now to change from mechanical degrees to electrical degrees is P, which is your pole pairs times electrical. Right. So electrical degrees is P times mechanical degrees. Then they can say, all right, you've got 9 slots per pole. Therefore, C will be 180 divided by 9, which is 20 degrees electrical. So directly, because per pole means you are going from a north pole to a south pole. And then as you remember, KD is equal to G dash sine G dash Psi over 2 over G dash sine Psi over 2. Now G dash is the number of slots per pole per phase. So because we need the number of poles, it's 2 times the pole pairs. And so, okay, that is slots per pole per phase. And G is just S divided by 2P. And then KD, KP is cos of epsilon divided by 2. Now epsilon depends on the number of slots that it's short coded. So if it's 1 slot, then epsilon is Psi. And if it's 2 slots, epsilon is 2 Psi. And then if we've got harmonics, KD for a certain harmonic is sine NG dash Psi over 2 over G dash sine N Psi over 2. And the same for KP will be cos N epsilon over 2. And with this, you should be able to solve all your problems regarding window factors, winding factors. Okay, today I want to start off with alternators. First of all, it is doubly fed. That means it's got 2 supplies. So let's do it like this. You got your rotating part, that's got DC. And your 3-phase winding is got AC. And then if we look at the equivalent circuit, we have the induced EMF here. Then we have XS and RA. armature resistance and synchronous reactance. Now, XS is the sum of your two X synchronous reactances that you've got. And now if you look at the equation, this is V, that the current is flowing out, and this is E. So we can say that E angle delta is equal to V angle 0 plus IA ZS. ZS is equal to RA plus JXS. Now, we've got two types of power. We've got the developed power that's inside the machine. And the output power, which is the output of the machine. Right. Now, first of all, let's look at the phasor diagram for this. Now, let's say we've got a lagging power factor. And R is negligible. That means we have the voltage and the current lagging. By an angle phi. Now, remember, when we don't have any resistance, this current Ix will be perpendicular to the current. And that means that is our induced EMF, and that is the load angle. Right. Now, the current can be lagging. It can be unity power factor. In that case, it means I is in phase with the voltage. So there we have V and IA, and now perpendicular to it will then be Ix. And again, that is our load angle and the induced EMF. Then we get a leading power factor. That means we have induced voltage, and there's a current leading by an angle phi. Now again, remember, this must always be perpendicular to the current causing it. So it should be in that direction, which is IAXS E and delta. By this you can see for a lagging power factor, E is bigger than V. For a leading power factor, E is less than V. Now that was the easy part if it's only reactance. If we now include the resistance, uh, well, then our lagging power factor would be again like that. Now the voltage IR, come on, will be parallel to IA, and again perpendicular to that will be IXS, and that'll give us induced EMF. That portion there is IZS, so that is delta, and that is phi. Now the same goes for unity power factor. Then that will be IR, and IX, that will be IZ, and that is E, and our angle phi. Yes, this is crazy pencil. Then for a leading power factor, we will have, then the volt drop will be IR, IX will be perpendicular to IR, that will be IZ, and that is E. That's delta, and that is phi. Oh, somebody in the waiting room. So let's look at the developed power and the output power. Now, first of all, we take E angle delta is V angle 0 plus IA ZS. Now we want to make IA the subject of a formula. So that means it's E angle delta minus V angle 0 divided by Z angle beta, where beta is the impedance angle of Z. Now we know that S is V times IA's conjugate. So this we can say is E divided by Z angle delta minus beta minus V over Z angle minus beta. So the conjugate then will be V times E over Z at the angle of beta minus delta minus V over Z angle beta. All right, this is output. I want the induced or the developed power. So the developed power has always got to do with E. So here we can say that it is E into E over Z cos beta minus delta minus V over Z cos beta. And the same for, that's P. Q, your reactive power, will be E into E over Z sine beta minus delta minus V over Z sine beta. Okay, now let's look at the developed power, output power, sorry. P out is V times the conjugate of the current. So that's V E over Z cos beta minus delta minus V over Z cos beta. And therefore Q out is going to be V E over Z sine beta minus delta minus V over Z sine beta. Right, have you got that so far? Okay, now normally all we have to do is we calculate, let's say we've got a 10 MVA 3300 volt star connected alternator with ZS is equal to 1 plus J5, say for instance. Now we have to calculate the developed power. First of all, the induced EMF, then the developed power, current and whatever. So we start off with IA is S divided by square root 3. We line, and that's 10 times 10 to the power of 6 divided by square root 3 divided by 3,300. Okay, that is 1,749.55 amps. I think maybe the chosen impedance is a bit high. Let's make it 0,1 and 0,5. So now E angle delta is V angle 0 plus IA ZS beta plus or minus phi. And let's say the power factor was 0,8 lagging. So V 3300 divided by square root 3. Square root. That'll give us, yeah, what for now? 1905,2. 1905,26 angle 0 plus 1749,55 minus 36,7 times the impedance is 0,1 plus J 0,5. So that gives us gives us a voltage of 2638 at an angle of 13 degrees. So now, if we want to develop power, we can say that it's E I cos of the angle between E and I. That's the shortcut method. So that means we've got 2638 times 1749.55 cos of 36.87 plus 13. That gives us a current per phase. Mm-hmm. 2,975 times 10 to the power of 6. Now that is watts per phase. So if we times it by 3, we get 8,924 megawatt in total. Now if we use our long formula, then we can say that it is E into E over Z cos beta minus delta minus V over Z cos beta. So that is 2638. Let's see what is 0.51. All right, so cos of 78.7 minus that 13, which is our load angle, 1905.26, 0.51 cos of 78.7. Okay, let's see. Right. Nee man, wat maar werk. 2, 6, 3, 8. Now why does it give me a little bit more? I think maybe there's a mistake somewhere. Let me just check again. Okay, the same answer. Okay, be that as it may, I'll check. Now, if we have to draw the phasor diagram for this, no need for it to be on scale. Power factor is 0.8 lagging, so it's minus 36,87. Right, so that's E, IR, IX, V, IA, and delta. So that's our phasor diagram. And now, let's say we want to know what is the voltage regulation. That will be E minus V divided by E. So that 2638 minus 1905,26 divided by 1905. Oh, my bad, it should be V, not E. So it is 3. It gives us 38,5%. Okay, have you got it so far? So in the test, I will ask you 1 or 2 questions on KD and KP, and 1 or 2 on alternators. So there are 2 ways to determine the voltage regulation. One is the synchronous impedance. And 2 is the Rother's method. For now, I think we're only going to do the synchronous impedance method. And that's the way that we do it. We calculate E first. Once we've got that, we can determine the voltage regulation. Now I want to see. Okay, I'm going to stop the recording now.